Good evening, welcome back to the classification of elements or periodic table. Today we will see the ionization potential or ionization enthalpy. Earlier we used to call it ionization potential IP. Now it is renamed as ionization enthalpy. Before going this thing, yesterday we have seen the atomic radii and atomic ionic radius variations and all. In that the last variation is the transition elements, that inner transition elements F block. That is also holds good for the same the lanthanum to lanthanum, but only two exceptions, that is europium and ytterbium. They will not follow the general rule of the from left side to right side, the atomic radii is coming down, that these two are not the holding the not accepting the general rule. Then in the D block, some more this thing is zirconium, hafnium, niobium, tantalum, molybdenum, and these two pairs, molybdenum and tungsten. These pairs also behave similar. So while you have to make it out, the separation of the elements is very difficult. Their properties is almost similar. That is zirconium, hafnium, niobium, tantalum, and molybdenum and tungsten. So if you see the basic strength of hydroxides from cesium to lanthanum, coordination, there is a coordinating bonding is more, covalent bonding character is more, so basicity will come down. That means cesium hydroxide is more basic compared to the lanthanum hydroxide. That is the general this thing. Now the important, the most of the time, this ionization enthalpy, ionization potential. Listen very carefully. See, most of the elements are either the solid gas or liquid or gases. But the ionization enthalpy or ionization potential, what we call it is, it has to be first, if it is solid or the liquid or gases, it has to be brought down to the gas state. If it is gas, okay. If it is liquid, it has to be gases. If it is solid to liquid, liquid to gas, it has to be brought down. Then it is to be atomized. First gas state, then atomized. Atomized gas state element, which is represented by normally Xg, is to be, one electron is to be taken out. X plus gas and electron. The energy required, not all the energies, whatever from the gas, solid to liquid, liquid to gas and atomization and all, we are not considering. A gas state atom, electron removing from a gas state atom is called as a ionization enthalpy. That also the first electron. There may be any electrons we are removing, but first electron is first ionization potential or ionization enthalpy. Second is second, third is third. So further, if you want, X plus gas state gives the X plus 2 gas state plus electron. This is called a second state. Okay. Now, how the trend represents that 1 to 60, their ionization potentials or ionization enthalpies are variations were noticed, and the graph, the very systematic. So if you see, I will start first with the lithium and all. Lithium, then previous to lithium is helium, previous to helium to previous is hydrogen. Say removing hydrogen, electron from hydrogen, then compared to helium is requires much more energy. Why? This is half filled, already high. This is much more high because it is fully filled. Here it is 1s1, it is 1s2. Removing electron from a filled orbital is very difficult. So ionization potential of helium is very high compared to hydrogen. Here it will be very deep because 1s2, 2s2, 1s1, 1s2. Here it is 2s1. 3 electrons. Lithium is 3. So easy to remove. Ionization potential of the lithium is low. Then comes to next, when we will go to the beryllium. Beryllium is 4. That means it is 2s2. It is slightly more than lithium. Then we will go to the boron. Boron is again, it starts with the 2p, 2p1. little less, but slightly more, but little less. It will not come very high. If you are going on like this, boron, carbon, nitrogen, oxygen, fluorine, here neon is very high. Again same fully filled. So carbon it is increasing, nitrogen it will increase. Why nitrogen is increasing compared to oxygen? This is half filled. Here again 4 electrons in the p orbital. 4 means one is joining in the another one. So oxygen ionization potential will be compared to the nitrogen it will be lesser. Fluorine again it will go, neon it will be the highest. So you can see if I am plotting the 1 to 60, a beautiful graph will be there. That is atomic number and IP, ionization enthalpy. Ionization enthalpy values, if I am graph putting, this is hydrogen, this is helium, hydrogen. Coming back to down is the lithium, then slightly lithium, then beryllium, then beryllium, then boron, P, slightly low. Then boron afterwards again it will go back to the carbon slightly high. Carbon, then nitrogen is very further high. Oxygen will come down. Then fluorine will go up. Then it will go to very high value, that is neon. If you see helium, neon, then argon, krypton, xenon, like this will be the highest values. So many in the bottom and all these things. So if you see, it will be lithium, the next will be the sodium, lowest, another one is the rubidium, cesium. The highest values if you see helium, neon, argon, krypton, xenon. 18th group is highest, whereas the lithium, sodium, rubidium, cesium. First group is the lowest IP value, because the S1S means NS1, 1S1, 2S1, then 3S1, 4S1, 5S1. Here it is the 2P6, 3P6, 4P5, 4, all P6 is this one. This is the trend. So very beautifully you can explain, and many questions are coming on this. So that is this thing. Then comes to this can be represented in different ways also. Slightly clumsy here. So I can write once again in the one more graph, same atomic number Z, enthalpy, ionization potential, lithium to beryllium, then comes to boron. More clearly I am writing boron, then comes to the carbon, going to the nitrogen, coming back to down to the oxygen, I already explained. Then it will go to the fluorine, then it will go to the neon. More clearly this will be explained. This is atomic number, and similarly you can plot one more graph, that is atomic number same to the in the vertical group side. Lithium is the highest, then comes to the sodium, then comes to potassium, then comes to rubidium. Why? It is going outer orbitals, so easy to remove the cesium. Less ionization potential is means less energy sufficient to take out the electron from this. Lithium is highest in a group, in a period, the first group from top to bottom, and this will be the across a period it will be like this. So that will be the normally the ionization potential. So ionization potential, in addition to ionization potential, there will be ionization potential. There will be some more terms, like the most important thing is electron gain. We used to call earlier it is a electron affinity. Now here recently the terms are revised. Electron gain enthalpy. Electron gain enthalpy. Here many books, if you see old books, it will be the electron affinity. Affinity. That means the energy which is released when an electron is added to the gaseous atom. So here we will see tomorrow electron gain enthalpy, and then electron negativity also will be there. Then that's all. We can see the valency and all. Okay, thank you.